So, hello everyone, I'm Inel, and this presentation was actually my Java user group Bosnia and Herzegovina meetup presentation, where initially I forgot to hit the record button, and so I took the chance to re-record it in English. So hopefully, any English-speaking people can maybe find it useful. So first of all, let me introduce myself. My name is Inel Pandzic, and currently I'm working at Infobip as a software engineer. I'm blogging at inelpandzic.com, and I'm a Bosnian Java user group co-organizer. Also, sorry about the background noise you could hear. Those are my laptop fans. It's a little bit hot in this room, and MacBooks are certainly not CPU cooling champions. So the goal of the presentation is to try explaining a few things about the JVM. So first, we are going to set some context. And to see what is really meant when we say the JVM. After that, we are going to cover main JVM components. So the class loader, the loading of our classes, runtime data area. It is basically JVM memory management, and execution engine. So the component which runs or executes our bytecode. So before we start talking about the JVM itself, I think it will be useful to show some wider context, so the complete Java platform. So Java is released in 1995 by Sun Microsystems. James Gosling is the original language architect, and it was basically designed as a managed OOP imperative language, where one of the main goals was a write once, run everywhere language. So in order for Java to be a write once, run everywhere language, there should be some component or a runtime which could read one source code and run it on different architectures or different platforms. This component is essentially the JVM, so the Java Virtual Machine. But besides this, the terms that go with the term Java, of course, besides the JVM, are also GRE and JDK. And the question about the differences between these terms is pretty popular on Stack Overflow. So first, there is of course the JVM. The JVM, so the Java Virtual Machine or the runtime. Next is Java Runtime Environment. So this is the core environment needed to run a Java program. So it is a different install for different operating systems. So GRE contains the JVM itself and core libraries and tools needed to run a Java application. So let's actually see this. So here I can go to library Java home GRE, and so this is the content of my of the Java runtime environment for my macOS operating system. So we can see the libs. Sorry. So these are the libs, core libs that are loaded that are present in my install of the GRE. And one of the main, the most important certainly is this rt.jar. rt.jar basically contains the core Java language libraries. Also, there is management containing everything from I don't know, JMX, flight recorder, or similar. And besides the libs, there are also tools that are needed, and most important one is of course the Java tool. So the Java tool is used for running our Java apps. So you can see you can say Java my app, and it will run your Java app. Besides the Java tool, there is also I don't know, key tool. It is used for it is used for security certificates. RMI registry, it is used for Java RMI support, so remote method invocation, and lots more. So after the JRE, we also have JDK, so the Java Development Kit. JDK is basically GRE plus some additional tools and libraries which are needed for developing Java applications. So we can also see this here. If we go just one step back, so this is my Java Development Kit. And of course, besides the GRE, there are additional tools and libraries. And you can see the libs. So besides the core libs that are loaded, that are present in GRE folder, here we can see additional libs. For example, JConsole, or the lib for the J shell, or the Java REPL that came with Java 5. Also, there is mission control stuff, Visual VM stuff, and some other. But the big difference between the GRE and the JDK is actually with the bin folder. So here you can see a lot more tools that are present for the Java development. So of course, besides the Java tool, which is also present in the GRE, or RMI registry, there is also Java C tool. So the Java compiler. We have Java doc tool. JConsole, the J shell. I don't know. There is a lot more here. JStat is used for monitoring purposes, also as JVisual VM. Serial variable tool is a tool for generating serial version IDs from existing compiled Java classes, and a lot more. So this basically describes the Java platform as a whole. Okay, so when we say JVM, we generally mean three things. So the JVM is first and foremost a specification. So this specification essentially says that JVM is an abstract computing machine, which means it has its own instruction set. This is our bytecode instructions, and it manipulates parts of the memory at runtime. The JVM does not know the Java programming language. The JVM only knows the specific binary format, or the .class file, the .class file contains the JVM instructions, so the bytecodes, and other class metadata that we will see later. So the .class file is a result of compiling .java file. So when we compile .java file, we get a .class file, and this .class file is run then with the Java tool, Java command. So the JVM is also an implementation of this specification, and certainly the most popular one is the hotspot JVM. The Zulu implementation is also popular, and Graal VM also. Graal VM is based on hotspot, and it is becoming increasingly popular. So Azul Zing is a proprietary implementation, and is generally used for low latency systems where the heap can be hundreds of gigabytes. And finally, the JVM is a runtime instance. So this essentially means that when a Java application is run with the Java command, this essentially one JVM is instantiated. Each Java program is a JVM instance for itself. So, what I'll be looking at now is some block diagram of a complete Java virtual machine with a complete platform overview. So first of all, we have the source code of our application, and it is this .java file. By compiling this file with the javac command, we get a .class file, and this class file is actually contains the bytecode instructions that will be run, and of course some additional class metadata. So when we run this .class file with the Java command, this will instantiate the JVM, which will then load this file. But before loading this file, it will first load the core Java libs, which we saw in the GRE /lib folder. Then it will load our .class file. It will then allocate the necessary memory for all that. Execute our bytecode instructions by calling native libraries, and finally, when we return from the main method, from the public static void method, the JVM as well as the process itself will be terminated. So this is a somewhat complete flow or a life cycle of a Java program. So the primary components of the JVM, which we will cover in detail, are the class loader, runtime data area, and the execution engine. Class loader is a subsystem that loads all the necessary files from usually the disk. It is a disk, which then verifies those files and ultimately places them all in the RAM memory allocated for the JVM instance. Runtime data area is actually memory allocated to the JVM process, and that the JVM divides into these sections and manages all at runtime. And execution engine is a component that sequentially executes all bytecode instructions it encounters. Garbage collection is also part of the execution engine. And we have a native method interface. So although JNI is always part of the JVM diagram, it is not necessarily an integral part of the JVM. So vendors may or may not support JNI. JNI is an interface that allows the JVM to call some native libraries, which are written in, I don't know, C, C++, or even assembly. And also it allows JVM to be called by the native libraries. It is used in situations when we cannot write everything we need in the JVM language. When we need some specific functionality of the certain architecture on which the JVM will run. We will focus here on these three basic components mentioned above. So the class loader, the runtime data area, and the execution engine. And now we will zoom in one by one. So at the very beginning, the JVM needs the files that will be executed, and this is a task for the class loader. So the class loader links and initializes a .class file that represents the class or interface that was referenced for the first time at runtime, not at compile time. So when a class or interface in runtime is needed for the first time, for example, we call the static method on a class, or we instantiate an object of a class, the class loader looks for that class and loads it into memory. The initial start, so the loading of initial classes starts before the execution of the public static void method, or the execution of this method will actually start the loading process. Will start the initial loading process. So the chapter 5 of the JVM specification talks about loading class files. Loading happens in three phases, which are loading itself. So this is searching and finding a class on disk, usually on the disk, and loading it into JVM memory. Linking phase verifies it is verifying the correctness of the loaded file, allocates the memory for static variables. Variables are set to their default values, and loads all referenced classes and interfaces. And in initialization phase, it essentially initializes all static variables to their real values, which we set in our code. We will now go through each phase in detail, starting from loading of the class. So, the loading phase looks for a physical.class file and loads it into memory. Loading is triggered when we instantiate a class. Also when calling the static method on a class. Also when reading static fields. Here I have to be a bit more precise. So when we say reading static fields, it is not this does not mean reading a compile time static field. So when we read a non-compile time static field, then the loading will be triggered. The reason for this is that the compile time static field. So those are the fields that are static and are initialized with the constant expression. Those fields will be loaded and put in the class metadata file itself. So they will be present in the constant in the constant pool of the file. Maybe to show this will be better. So this is constant. This is compile time static field. So we have public static final num equals 10. So this is a compile time static field. This means is that it is final, so it will never change, and it has a constant expression. So the constant expression is this literal value of 10. If you say, for example, something like this. This is not a constant time field, because this get num is not known at compile time. After this, when the subclass is loaded, so the loading is triggered when the subclass is loaded. This means if the current class that is being loaded extends some other class, then that superclass will be loaded first. Then, and after that class is loaded, then the current class will continue to be loaded, I can say. And also when we use reflection, the loading will start. There are multiple class loaders actually, and each loads files from specific repository or location. So the first is the Bootstrap class loader, also called primordial. So the Bootstrap is the parent of all subsequent class loaders, and it only is implemented in C, and the only one which is implemented is in C and C++. And it loads core Java libraries from the /gre/lib location. So core libs like rt.jar. Next is the Next is the extension class loader. So extension class loader is loading standard Java extension libraries from /gre/lib/x location. These libs are like I don't know, nashorn.jar. Nashorn is a jar for running JavaScript inside of the JVM. And this location, so the location of the extension class loader can be configured with some system property. And then after that we have application or system class loader. So this is the class loader that, which loads the classes that we provided. So these are our application classes. The location of this, the location where application class loader will look for our classes is the value of the class path environment variable, or when we specify Java command line dash CP option. In addition to these, there are also user-defined class loaders. And these are the loaders that we implement actually. So it is you can just inherit java.lang.class loader class, and you basically have a class loader. They are really rarely used, and generally they are useful in cases where we have some specific location of our classes. So we can, for example, load them from the database, or grab them from the over the network, or when we simply need some specific loading, some specific way of loading classes. They are commonly used in some core server implementation. For example, Tomcat uses its own specific class loader. Vertex, I believe, also has something similar going on. So this is maybe the most important part. So the files are loaded according to the so-called parent delegation model, and it represents the following. So first of all, you can notice this parent-child relationship between all the class loaders. For example, the application loader is the application class loader. Parent is the extension class loader, and so on. And the bootstrap is the root. It is the parent of all subsequent class loaders. So when asked for some class file, the class loader will immediately delegate the search to its parent, and so on until the bootstrap class loader is reached. After the bootstrap class loader searches for the class at its location, and if it finds the class, the file will be returned. If it doesn't find the class needed, it will pass the search on to its child, which is in this case the extension class loader. So if this one doesn't find it, it forwards the search all the way to the class loader where the initial request came from. So, for example, we have a request coming to application class loader for some class. The application class loader will immediately delegate the search to extension, and the extension will delegate it to bootstrap class loader. When the search request comes to the bootstrap class loader, it will try to find it. If it finds the class will be returned. If the bootstrap doesn't find the class, it will then delegate the search to its child, so the extension class loader, and so on until the class is found, or to the point to the class loader where the initial request came. So it doesn't have to be application class loader. Maybe it is some user-defined class loader as well. The primary reason for this is the security. So the JVM gives preference and trusts more location of the higher class loaders. So, for example, it trusts locations that are read by extension class loader more than the application class loader, and so on. The location of the bootstrap class loader have the highest preference. So if you're looking for a class, it will first see if there is the class in the bootstrap location. If not, then check the class extension class loader, and so on. So if the class is not found successfully, then the java.class sorry, if the class is found successfully, then java.lang.class object is instantiated for that class, and that object is actually output of this loading step. So the class object contains all the metadata about the class itself. So these are the method names, whether it is a class or an interface, a list of interfaces that, for example, it implements, and everything else. And if the class file is not found, then the runtime class not found exception is thrown. After loading, the linking phase occurs. And as the input for this phase is the class object that was instantiated in the loading phase. So this is the most complicated and the slowest phase. So the linking phase is contained from several steps, where the first step is the verification process. So this step is the most complicated in the complete class loading flow, class loading phase, and it lasts the longest. Here, the correctness of the .class file is ensured. So does the code violates the Java specification? Maybe is it generated by the correct compiler, and similar reasons. In general, all detailed security checks are performed here. Some of the checks that are done are that the final class does not is not extended, or that maybe that the final method is not overridden, that there are no illegal overloading methods. It checks bytecode validity and much more. A bytecode verifier is a component that performs this verification. If the verification fails for some reason, the class is rejected and the java.lang.verify error, I think, is thrown. After successful verification, the preparation phase follows. So memory is allocated for static variables, and they are set to their default values. If you, for example, if you declared some boolean static field, then it will get the default value of false. If it is a matter of creating a class instance, also instantiating a class, then instance fields are also set here. Their instance fields are set after the static ones are set, of course. And this happens throughout the hierarchy, throughout the whole class hierarchy. So first we prepare all the static fields of the whole hierarchy, so the superclasses, and only then the instance field also first for the superclasses, then the current class that is loaded. And this is the last step in the leaking phase, so the resolution. This is where loading of all referenced classes takes place. So, for example, if our class X uses some class Y, in this step, the referenced class Y is first resolved. Initially, all references are so-called symbolic references or logical references and are stored in the constant pool of the .class file. When referenced classes are loaded into memory, then the symbolic references are replaced with direct references at runtime. A direct reference is actually a real physical address of the reference class on the heap. This is generally called dynamic linking because all classes are loaded and resolved dynamically at runtime. The resolve phase does not necessarily have to be performed after the preparations, after the prepare phase. It can also be performed somewhat in parallel with the preparation phase, or it can also occur after the last initialization phase. This all basically depends on the JVM implementation. And finally, we have the initialization phase, where the static fields, the static variables, are now set with their values that we have specified. So default values from the preparation phase are now overridden. Also, static blocks are executed at this stage. But when it comes to interfaces, they will not be loaded. They will be loaded, but will not be initialized. Interfaces will be initialized only if a static method is called on them, and we know that static methods are available only from Java 8 and onwards. So with this, we finish the class loader component. There are more details here that I failed to mention, but I leave that to you if you are interested. So let's move on. So the next component of the JVM architecture is the runtime data area. So this is not component that does something like a class loader. This is simply a block of memory managed by the JVM and by various JVM components. So when the JVM process starts, like any other process, the operating system allocates for it one chunk or one block of user space memory or high memory. The JVM further divides this block of memory into different sections, which are method area, Java Heap, JVM stack, program counter part, and native method stack. As we see in this diagram, there are memory sections that are shared between the threads and that are per thread. The sections that are shared between threads are method area and heap. So the heap. When we say the heap, by default we mean the Java managed heap. So Java objects are created and stored on the heap. So the instances of the class that we create with the new operator. When we say an object, we simply mean the instance data given to that object. This is the basically values of the instance fields. In addition, of course, we have a couple of headers, such as whether the object holds a lock or not. There is also the wait state, so the condition queue of the threads waiting for the lock, and much more. In addition to our Java objects, there are Java objects created by the JVM, which are also stored on the heap. These are the class objects which have been loaded by the class loader, and also class loaders that are instantiated are also stored on the heap. When we tune the JVM memory, we usually do it with heap memory. The XMS option sets the initial size of the heap, and XMX sets the maximum size of the heap. So the method area, unlike the heap that stores object data, the method area stores class data. We can simply say that this is the data of the class itself. So the value that is available to all, these are the values that are available to all instances of that class. These are basically static fields. All instances of a class will say have a pointer to the class object in the method area. A couple of things kept for each class class data are so it is the meta info. So this is the full name, fully qualified name of the class itself. Also the names of the superclasses or super interface. Whether it is a class or an interface, whether it is a final or abstract, and all the stuff. Class object reference. So the relationship between the class object on the heap and the class data in the method area is bidirectional. So for example, a class loader, when loading a class, first checks if there is a class object on the heap for this class. And it does this the class loader checks this by looking in the method area and the class data for that object So if there is a pointer, if there is a pointer to the object, if there is a pointer to the class object on the heap, simply it will return that address. It will not do the loading because it is already loaded. So we also have field info. So this is the field name, field type, type modifiers, whether it is a final or static, or also access modifiers, whether the field is private or public or similar. In general, all the information can be obtained through a class object of this type. So the class object, that is the java.lang.class object, internally actually reads the class data in the method area. And we also have a runtime constant pool. So we know that .class file contains a constant pool section of the file. So there is a section of the file that is called a constant pool. And runtime constant pool is actually runtime version of that pool. The constant pool contains various literal values. So, for example, when we earlier mentioned the compile time constant pools, constant fields are stored in constant pool. It also stores symbolic references that we mentioned earlier. Also string constant pool is located here, and some other stuff. And also we have method info, so info about the method itself. So the name of the method, the return type of the method, parameters and parameter types, as well as the bytecode of the body of the method. Method info also holds info about constructors as well. Since class data is shared between threads, and it is created when the class is loaded, so this means that the whole loading process must be thread safe, of course. In Java 10 we also got something called class data sharing. So this is a feature that allows different JVM instances to share class metadata. This is something like shared metadata for all JVM processes. So this allows much faster startup because the JVM does not necessarily have to reload all the classes that were loaded by some previous JVM process. So besides the shared memory, the next three sections are per thread. So they are only visible for individual threads. Per thread sections are the Java stack, native method stack, and the PC registers or program counter registers. The stack is essentially the same as the operating system stacks. So the stack, so it is a stack of method calls or method invocation states. As with the operating system, Java on the stack stores stack frames, or as it is also called activation record. So stack frame contains all the data regarding the method calls. So these are the arguments passed to the method, all the local variables of the method, the return address where the method will be returned, and much more. So the JVM limits the stack size, and the default stack size is 512 kilobytes for 32-bit architectures, and 1 megabyte for 60-bit for architectures. We can configure stack size with various JVM command line options. When the stack limit is reached, then we get probably the most famous exception, so the stack overflow exception. Or maybe then I will bet that the null pointer exception is the more popular, at least for me. So in addition to the stack, there is also a stack only for calls to native methods. So methods written in languages like C, C++, or assembler. When we use the Java native interface, calls to these methods will end up on the native method stack. So when the native method stack is called from Java, the Java stack frame will simply point to the native stack frame. So here, in this picture, the last frame or the top of the T2 stack will point to the T2 native stack on the native method stack. Some JVM implementations have the same stack for managed and native stacks, and then they are using something called stack unwinding, which is used to link all the different frames. Different frames meaning managed and native stack and native stacks, native stack frames. So the program counter serves the same as the CPU program counter. So it is the value of the next instruction. In the JVM, this program counter value is the pointer or address to the bytecode of the method in the method area, which we mentioned. What is also important in all this is to emphasize the differences, the difference that can generally be confusing. So the difference between native and Java managed heap. So the JVM essentially maintains two parts of the memory. So the native heap memory, also called as C heap or off heap or system heap, and the other part is the Java heap, so the Java managed heap. The Java heap is what is meant when we say the heap, and all the heap JVM options we have are related to Java heap. As we know, all Java objects are stored here, and everything is maintained by the garbage collector. By the garbage collector, we mentioned it. We will talk about it a little bit later. So if we do not set the limit ourselves, the JVM will assign a default limit as well as the initial size of the JVM heap. Also, when we do a heap dump, it only applies to Java heap. The native heap is the part of memory where the JVM stores everything else. So the method area, the stack, and the program counter registers, and the native method stacks are all stored on the native heap. And there are other things as well which are stored on the native heap. For example, JIT compiled code is stored on the native heap. Memory leak bugs are generally tricky, but also generally happen without Java objects. But memory leak can also happen in native memory, and it is even harder to resolve. Primarily because when we do a heap dump, we only see Java heap. That is, the JVM does not monitor native heap as closely as the Java heap. And prior to Java 8, the method area was also located in the Java heap. So that part of the Java heap was called permanent generation or permgen, and had a max limit size. There are tweaking options for permgen, of course. The problem was that in this way the class metadata was mixed with Java objects, and besides that, the common out-of-memory error was the permgen no longer had room to load and store classes. So the permgen had max size, and when there is much activities loading new classes, it can throw out of memory error. Java 8 completely removes permgen and introduces a new part called metaspace, and metaspace stores class data. That is, it stores everything that is in the method area section. The primary difference is that metaspace is now located on the native heap, not Java heap. So it is located on the native heap, and it can basically grows as much as there is system memory, or as much as the operating system can allocate memory to the JVM process itself. And also important part is that garbage collection was much improved by deleting the permgen. The last component we will talk about is the execution engine. So this is a component that actually reads bytecode instructions, translates them to native CPU instructions, and which are then executed as such. All these components of the execution engine are topics really for themselves, and here I will only give some high level overview. So when the JVM application is started, the instructions are initially interpreted, and of course the interpreter is used for that. So Java interpreter does not differ much from typical interpreters in interpreted languages like Python, Ruby, PHP, and others. The interpreter reads the bytecodes line by line, and immediately executes them by of course translating them to machine code. So Java interpreter is not as advanced and as interpreters of exclusively interpreted languages, and this has been done so consciously. So when a method is called frequently, then the so-called just-in-time compiler or JIT will kick in, which means that the method that is called very often, the so-called hot method, will be compiled into native code, and then when called next time, it will not be interpreted, but machine call will be executed directly. This, you might expect, gives Java applications a big performance boost. This does not only apply to the methods, but generally to the hot code path. It can be, for example, an if block within a method that is constantly entered. For the hotspot VM, by default, if the method is called, I think 10,000 times, it becomes hot, and it is then JIT compiled. This is why the name of the VM is the hotspot VM. In addition to the compilation itself, the JIT compiler does various optimizations of the code that it compiles, and there are really a lot of them. This method of optimization, so by monitoring program execution at runtime and optimizing it, is generally called profile guided optimization. And today's JIT compilers are so sophisticated that the Java code can actually be faster than native languages like C or C++. Technically, there are two JIT compilers. These are the C1 and C2 JIT compiler. The C1 is generally used for desktop application, and C2 for long-running serial application. And both of them do certain optimization. Today, by default, the so-called tiered compilation is on by default. Which means that C1 and C2 compilers are used. So first the C1 kicks in, and then the C2 kicks in. On the diagram, they are shown as equal, but essentially C2 compiler, C2 JIT compiler is the one that does all the super sophisticated stuff. Also, I haven't mentioned here, but there is also something called ahead of time compilation. It is simply the ability to compile Java classes into native code before execution itself. And the goal of this is to speed up the startup time of the Java application. And with ahead of time compilation, although the startup time will improve, but then we are losing this profile guided optimization at runtime. So that is basically a trade-off of using ahead of time compilation. And finally, since Java is a managed language, there is it allocates and deallocates memory for us. We do not have to do it manually, and for this feature we need a garbage collector. So GC is a mechanism that monitors Java objects on the heap, and when it sees that something is not in use, it will delete the object and free up that memory. In addition to deleting dead objects, it also moves live objects, so the heap is always well formatted, meaning that they are large chunks of free memory that can be allocated for some large large array, for example. In general, the way GC tracks dead objects is actually by tracking live objects and deleting everything else. A live object is one to which there are references pointing to. There are, of course, many more things that cannot be covered here. How GC divides the heap into different regions, and how and where generations of objects are stored. What are these generations? There are of course different GC algorithms, and there are serial algorithms, parallel algorithms, full GC or minor GC cycles, and much more. What I will only emphasize here is that GC does not cover only the Java heap, but also method area as well. It cleans class data that is no longer used. Cleaning of the method area or the native heap part is done when the full GC is performed. Just-in-time compilers and garbage collectors are huge topics in and of themselves. Here I just covered a very high level stuff. So this is basically it. So to summarize everything here, so we talked about the class loader and how class files are loaded, linked and initialized. Then we covered runtime data area. Here we saw how the JVM divides and manages its memory block. We have a Java heap, we have a method heap, and how all is managed. And last but not least, we covered the execution engine and how our bytecode is at first interpreted, then if called enough times, JIT compiled, and how everything is cleaned and managed, maintained with a garbage collector. Hope you find this useful, and if you did, please of course share it. If I got something wrong, please reach to me and we can discuss it. Thank you, and stay safe in these Corona times. Bye.